So what we have here is a spherical mirror, and the focus is right here, and the center of curvature, which is just, if you imagine extending this into a big circle, center of curvature is just the middle of that circle. That's gonna be double the distance of the focus. Um, I guess the reason why the focus is half of the radius, right? Half the distance from the center to the mirror. I think it's because, just through a lot of experiments, we've found that, hey, the focus ends up being, where like all the light gets focused ends up being half the mirror. But if you know anything about parabolas, they have their own focal points and ellipses and all that stuff. So maybe that's something you can think about. Here we got a man. Usually when you're doing these kind of problems, it's going to be arrows, but just so that you understand what's going on, I'm going to use a person and use different points on the body to kind of show you how the light's being reflected. Here's how you approach ray diagram problems. So, in general, the main kind of idea here is how light behaves with the focus. Let's say we shine a beam. Let's say right here, right? Like there's a beam from the head all the way to the spherical mirror, and this line is parallel to kind of the ground, or not the ground, but this middle line that's passing through the focus in the center. We call that the principal axis. So if you have light parallel to the principal axis, that light will bounce off into the focus, like so. So this is just the law of reflection, right? Because the normal at this point, if you think about the normal line at that point, the law of reflection tells us that, hey, the reflected angle, if you had a mirror, right? The angle, actually, I should just draw it like this. If you had an incident ray light, right? Light hitting a mirror, that angle of incidence from the normal will be the same as the reflected angle. So in this case, we have a curve, right? So there's not really one normal. Instead, if you zoom into the mirror, you get a really small section of that mirror that we can basically treat as like straight, right? And that will have that will have its own normal line, and thus it'll be be treated like a mirror, right? And you'll see the law of reflection. This angle will equal that angle. So, and hey, the normal will always be like pointing towards the center because of geometry, right? Because the tangent line, if you remember from geometry, like the tangent line is perpendicular to the normal line, and the tangent line and the radius, they meet and make that right angle. So this would end up being the normal. Point is, light's gonna hit the focus, and the opposite kind of happens, where if you have light that goes through the focus, and I don't have a ruler to really do this, but if you have a light that ends up, passing through the focus and hitting the mirror, that light ends up being parallel. So right here is where you'd expect the head to be. And you might be thinking, wow, his head looks inverted. And I'm going to show you that he will indeed look like he's upside down. I'm just going to use different parts. So if you think about the torso, right? The torso is going to be like this. It's going to pass through, it's going to get dicey. It's going to pass through the focus. And then it's also going to, pass through the focus directly. And that, light will then be parallel to the principal axis. And hey, now you have the torso forming. And you can do the same thing for the hand, right? You can do it for really any body part you want, or any point. And then this will be passing through the focus, and it'll end up being like that. And I've drawn a lot, but I think right here is where the hand is, like the tip of the hand. So it would look, I guess, like this. I drew it wrong. But you will see he will be upside down. He'll be inverted like that. So, hey, he looks like he's a bit shorter than he actually appears. As you get closer and closer and closer and closer to the mirror, your image will grow, right? Like you will grow, but you're also gonna get farther back. So I'm gonna replace this whole person with an arrow instead to show you kind of what I'm talking about. But the main idea is if this is C and this is F, like halfway through, right? If you think about an arrow, if I do, actually, yeah, let's do an arrow here. If I do my little fun, thing, you're gonna see that the arrow, I didn't draw things straight so you don't get it perfectly, but the main idea is that if you're standing at the center of curvature, hey, you're gonna be the same height, but just inverted the other way. As you get closer and closer and closer, you're gonna get bigger, but your reflected image will start to go farther and farther to infinity. That is actually exactly kind of what this graph tells us right here. This 1 over S initial, or S distance of your image over 1 over the object distance, right? It looks like this, and these points right here are 1 over the focal length. So what is this telling us? Well, if our object distance gets closer and closer and closer to the focal point, right? So if the inverse of the object distance gets closer to the inverse of the focal distance, aka if F equals S initial, right? Because they're just both inverses. As we get closer and closer and closer to the focus, the 1 over, so I guess I should do this. I won't do limits because not everyone's in calc, but as S initial approaches or gets closer and closer to the focal distance, right? What we see is that 1 over S initial, right? What we're graphing on the y-axis, that gets closer and closer and closer to 0. So I guess that should say 1 over S initial gets closer to 0. Well, how do you get a fraction to be closer and closer and closer to 0? Well, the denominator needs to get bigger and bigger and bigger and bigger. So S initial, so therefore, or I say initial, that's a bad habit. I should say image. S image, not like I should as in it's good for teaching, like no, it's literally S image. But S image is going to approach infinity. That's why you can't really see anything when you're standing at the focal distance. Because what's literally happening at the focal I actually have to think about some more. I was doing this problem where you're standing at the focal distance. I need to think about it some more. But the whole idea is when you're standing at the focal distance, you can't see anything. Your image, theoretically, would be like an infinite distance away. You can't really see anything. But everything is so zoomed in and magnified because, your magnification, right? Well, I'll make maybe a separate video on magnification. It's just the ratio between the image distance versus the initial distance. And you can think about why that is. But the whole idea is that, hey, if your image is super, super, super far away, you're magnified, right? And basically all the image distances are going to be really big, really, really, really big. Because that's what magnification is. Magnification is just the ratio of the image distances to the object distances. So if you think about when you're looking at a curved mirror, right? The distance from like my nose to my, I don't know, this bear on my hoodie, right? That distance, if I'm getting closer and closer and closer to the focal point, my magnification's going up. So that distance on the image, right? This distance that I see on the image is going to be much bigger. As you're standing on the focal length, that this distance would theoretically be infinite, right? And I don't even see anything. Like it's everything's so zoomed in, I can't see anything. But that's kind of the idea with focal length. And if you go past F, well, now you're not even going to get a real image, right? all the images you see up to this point are considered real images, because what you're literally seeing is you're literally just seeing light being reflected. Like you're seeing that reflected light forming that image. It's kind of crazy. I guess it's kind of like a mirage, right? Like you're seeing that reflected light form an image. But once you get past the focal distance and get closer and closer and closer, you know, you can't really see the light, because if you're standing right here, it's like, well, this light that is going straight, it's going to go kind of past you, and then this light right here. So you can't really see behind you, right? But if you're standing right there, what you will get is a virtual image, because this light, you essentially get light being reflected. And if you were to follow this backwards, you would get a virtual image. That would kind of look like so, right? Because you would see the light seeming to converge all the way behind the mirror, even though light is not actually, like, light can't go past the mirror. It reflects, but it looks like that as a, it looks like it's converging behind the mirror. So for convex, it's kind of the same idea, but instead, for convex, you're gonna have, it's gonna look like light. So I should do it like this. So if oh my god, I need a new marker so bad. It's actually annoying me. But point is, if this is my focus right here, it's the same principles, but now the light is, if you think about light from the focus, like converging to that spot, it reflects like so. So, right, there's still that normal line. Law of reflection still holds, but now that light is going to seem to converge to a certain focus that we can't really see because it's behind the mirror, but it's going to seem to converge at a certain point. And, and then if you think about, well, light that is seeming to hit the focus, well, it gets reflected off like so, right? And you get a virtual image that is going to look, shoot, it should look bigger, shouldn't it? Wait, let me check. I might have messed up my diagram. It'll look smaller, which I guess makes sense. If you've seen these kind of mirrors before, right, you literally look smaller. So what you're seeing is a virtual image. Like that name, virtual images, that sounds kind of crazy. It sounds like a sci-fi thing, like a virtual image. Literally all a virtual image is light seeming to converge to a certain point so that this looks like a source of light, or it looks like it's reflecting light, but it's not. It's almost like an optical illusion. Like the light reflects, and the way we perceive light, I don't know, it's probably like a way we also just see light in general and like a brain thing. But yeah, it's almost like an optical, I guess it is an optical illusion. I don't know. It's just kind of cool. Hey, optical illusion. How cool is that? Optics. I don't know. That's maybe something I gotta look into. But this is kind of an intro into ray diagrams. Thanks for watching.